Everybody, this is Larry. This is day 21 of the May Leetcode challenge. Let's get started. Hit the like button, hit the subscribe button, join the Discord channel, whatever, hang out, and let's take a look at today's problem. Count square submatrices with all ones. Given an m by n matrix of ones and zeros, return how many square submatrices have all ones. Okay. Um, this seems like a way to count it. So n is 300, which means that n square is okay, but n is the input size, so the length, the entire size of the array is actually 300 square, right? And what that means to me is, let's see, I'm just pulling up a calculator because math is hard. So 300 square is 90,000. And we try to do 90,000 square, it's way too big, right? It's going to be like 8 billion, something like that. So we probably definitely need a dynamic programming with a linear algorithm, linear with respect to the total input size. And I think these examples are actually really great at illustrating what the problem's asking for. I think I had some reservation. But basically, there is a standard dynamic programming problem that lets you get the largest square that ends at that corner. So I think that is enough for us to. I think that's enough for us to count how many squares there are, in the sense that. Because what I'm thinking right now, and maybe this is a little hand wavy and I'm skipping ahead way too much, feel free to ask a question in the comments or something like that. But first of all, you need to figure out it is a little bit of a standard right now, or I don't know if it's a standard, but it comes up a few times for me anyway, finding the largest square in a submatrix. And the idea behind that is that the largest square behind some submatrix is, let's play around with this matrix. The idea behind here is that if you're looking at here, the biggest square that ends with by ending, I mean on the bottom right, and on the bottom right, this is 1, right? So this is the biggest square because it's by one square, so it's always going to be bigger than 1. Here it's still 1 and so forth, and you go forth. Here the dynamic programming is, well, let's say your biggest up to date now is 0, 1, 1, 1, 1, because you only have one row, so your square is going to be at most 1. This is 1 as well. Here, this is 1 again because it looks at the left, the right, and then the diagonal. And if they're all squares, that's when you are able to create a bigger square, almost like a Megatron now. But really, because this is 0, if you try to draw a square from here to here, well, you can't, right? Because, now we've all filled with 1s. So this is still 1. Similarly, here, we get 2 because, well, here it is 1, first of all, because if this is not filled, then you don't get anything. And then you look at the top, left, and diagonal, and they're both at 1, so then you could kind of visualize boxes where you have box here, 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 and here, and then you combine them to make a big 2 by 2 square, right? And then we do the same here. Here we look at here, that's a 2 by 2, but this is only 1 by 1 and 1 by 1. And if you draw it out, you have a box here, you have a box here, and then you have a 2 by 2 box, which is nice, but together you only fits a 2 by 2 box. So that's what I will have here. And then similarly, this is 0, this is still 1, this is 2 again, because 2 gets to look at here, it's 1 by 1, here's, 2 by 2, this is 1 by 1, 1 by 1. You could draw the overlapping boxes to prove yourself correct. It's going to take me too long to bring up MS Paint, but you could do that. Here, actually, the interesting one is that this becomes 3, right? Because this is 2, that means you could draw a 2 by 2 box that starts from this box to here, drawing the box here, and then here to this 2 means that there's a square from here to here, right? From this 1 cell to this 2 cell, and the same for 2 here. So if you draw the 3 boxes of size 2 together, you could and including the new space that we just added, you could draw a full 3x3 box. Definitely for your homework, draw that out and really prove to yourself why this is correct and this is true. Okay, so now we use dynamic programming to find the largest square that has an upper, oh sorry, that has a lower right corner at that box, right? So 2, 2, 2, 3, 1, 1, and a lot of ones in a lot of places. And the question is, how many squares are there, right? Well, actually, the thing that I noticed, and that was the part that I was worried that I was a little bit hand wavy, but now we're explaining it, is that, well, you can actually count this in a really easy way. It turns out, if you make the observation that if the largest square that you can make at that corner is 1, then obviously you only add 1 to the total. Same here with all the other ones. But what does a 2 mean, right? A 2 means that there are 2 squares that ends, and by ending I mean on the bottom right corner, 2 squares have a bottom right corner ending at that corner, right? Why? Because 2 here is the largest square, but it also means that there's a 1x1 square here, there's a 2x2 square here, and that totals to 2 squares. Similarly with 3, I mean, you can also mix the same argument with the other 2, but with the 3, there are 3 squares here because there's one 1x1 square that ends in this corner, there's one 2x2 square that ends with the bottom right corner here. And then there's one 3x3 squares that end the bottom right hand corner here. Okay, so putting all that together, the dynamic programming is probably the easy part relatively, only because, well, you should practice it, but I've been practicing it, so that's why it's a little bit easy for me. Okay, let's set it and let's be responsible. Rows is equal to length of matrix. Columns is equal to length of matrix of 0. And here, that's when I usually check to make sure that 0 is not an valid input. Otherwise, this will give you out of index error. And I've definitely made that mistakes before. Cool. And then now we just have to initialize everything to 0. In your language, this may be different. This just gives me a rows by columns matrix of zeros. And then now let's do a count, and then we return count as the final result. And so the goal for me here is just to calculate this matrix from this one and then sum up the result. But yeah, so for x is in range of rows, for y is in range of columns. dp of x of y is equal to, so how do we convert this, right? Well, we just take the smallest number from the last 3 and here, and then add it to 1 if this is a 1, right? So if matrix of x of y is equal to 1 and maybe 1 string, let me double check. Sometimes the input is a string and not a number, but in this case it is the number, so okay. So dp of xy is equal to the minimum of dpx minus 1, y, dpx minus 1, y minus 1, dpx y minus 1. Those are the 3 corners. And here, in theory, you have to check our bounds. So what we can do here instead is just pad it by 1 more so that we don't have to worry about our bounds. But then in this case, we have to add 1 here for the padding. So add 1 to everything. So min of these 3 plus 1 will be what I like here. And I think that's good enough. Obviously, we don't do count, but just to visualize this, and okay, I could skip the visualization. But what I would normally do is I would just do this, and they'll be good enough because in the later loop we notice that we never need to update this again and we need to do the sum anyway. So let's run the code, and yeah, there are more test cases. There is, yay. Yeah, I think that's all that I need for this problem. And let's click on submit. Cool. Yeah, overall, what can I say about this one? So I would say this is not an easy problem. I think there are a couple of prerequisites to knowing this problem. And even if I do make it look easy, it's because I have experience of these similar problems. I think for me, the thought process was, okay, well, count square matrices in general, or the similar problem that it reminded me of was to count the largest square at that corner. And then from that, I was like, well, what does that mean? And then I got very lucky, I suppose, with the association that what I explained, which is that I got very lucky with the association with what I explained, which is that if the corner is of size x, it means that there are x squares ending at that corner. So sometimes you get a little bit lucky with a lot of practice, but overall this is a very hard problem. So if you did not get the logical conclusions that I came to immediately, definitely work it out and just practice a bit. And of course, I would also say that I made the dynamic programming typing and stuff like this really quickly and easily. But a lot of that is practice and experience. So really don't be hard on yourself. Just make sure that you understand every step of the way. And when your understanding is there, the coding will come easier. It comes to practice. The part that is tricky is making sure that you don't have to relearn the same thing that you thought you learned the first time. And from that is, you try to learn it correctly the first time, which is easier said than done, of course. In terms of complexity and space, for time and space, so time is going to be rows times columns because we look at each element of the matrix once. For space, this is also rows times columns, or of rows times columns. But and there's a video, I'll probably send a link below, but I have a dynamic programming tutorial on space optimizations, which is not that hard. But the idea is noticing that there is an optimization that we can make, which is that DP this row of DP answer only relies on the previous row, and as such, you can actually remove. You only need to keep track of the last two rows or something like that, and that will allow you to get all of rows plus column space instead. And it's something that is, for n is equal to 300, I'm not going to worry about it, or for each row is equal to 300, I'm not going to worry about it. But it is something to think about, something to talk about during an interview, as something that makes you look a little bit better in terms of interview. I think this, for me, I feel like this problem is a little bit too hard for an interview, but I don't know. Use of your own judgment for what that means. In terms of computer programming, I think this is, I wouldn't say it's standard, but the square thing comes up somewhat often for some reason. Not that often, but every time I see it, I'm like, oh yeah, it's they use the same idea, which is a little bit odd. But yeah, but that's all I have with this problem. Let me know what you think. Let me know how you did it. Let me know if you learned anything, and let me know if you have any questions. I will see y'all tomorrow. Thank you. Bye bye.